Okay. Last class we studied about this one, Mendeleev's classification. Correct, ma, Ganika?
Yes.
Hmm. Any doubt in Mendeleev's classification? Okay. See, was based on the atomic mass, correct? Okay. Mendeleev's classification was based on the atomic mass. Okay. Now, when you look at the Mendeleev's classification, last time we learned that Mendeleev had no knowledge, or at that time there was no knowledge about the inert gases, right? The inert gases were not known at the time when Mendeleev was doing the classification. But yet, the Mendeleev's classification could provide the inert gases a place for the elements when they were found later on. Did we talk about the merits that he proposed, that the empty spaces are opportunities and elements could be found out for those places? Did we all discuss about that?
Yes.
Okay. So when Mendeleev's classification was done, basically it was limited to this. He started classifying from group 1 to group 8. Sometimes in a group, there used to be two elements. He used to call, say, beryllium and magnesium both are present in the same group. He used to say that this is 2A element and this is 2B element. So in a box, if you can see, there is something in the top end left corner and something in the bottom right corner. He used to call this as like this is belonging to group 2. So he used to say this is 2A element and this is 2B element. Is that fine?
Yes.
Okay. Also, in his eighth group, he fit a number of elements. See, he fit iron, cobalt, nickel, copper. Later on, when we come to 12th standard, we will understand that almost all of these have got similar atomic sizes, and that's why their properties looked very similar. But the atomic masses as given, right? Uh, like the similarities in the chemical properties between iron, cobalt, and nickel reflected that probably these three would be present in the same group. So in Mendeleev's classification, there were two separate rows fitted into one, right? Namely 2A, 2B, likewise 3A, 3B. Are you getting the point, Ma?
Yes.
4A, 4B. Okay, this is one of the features. The Mendeleev's classification had only from 1 to 8. The group 0 was not present when Mendeleev did the classification. There were a lot of empty spaces left out, right? Like there was something, this place was left out. The scandium's place was left out. Similarly, there is gallium. Where is gallium? I need to find where is gallium. So gallium's place also was left empty. Okay. And in fact, when he saw an empty place, because the scandium was not known at that time, when he saw an empty place, he suggested that this element is probably not known today, but will be discovered later. And when discovered, this element would have mass more than aluminium, right? And as aluminium forms Al2O3 and AlCl3, this element, which would be found in the future, would also form E2O3 and ECl3. So he proposed the presence of some elements and which was found to be too real, actually. Okay, it was found to be very matching with the proposed properties. Okay. So some of the problems with Mendeleev's classification was that sometimes two dissimilar elements same sat together. For example, in today's classification, the elements zirconium and titanium have got no relationship. Niobium, antimony, molybdenum, tellurium have nothing in common. Chromium and selenium, nothing in common. Vanadium and arsenic, nothing in common. So probably he did not explore all the properties of the elements. Are you getting the point?
And he just arranged them with increasing atomic mass, but not according to the similar properties.
No, he did. But see, Ganeka, supposing I want to find somebody like Ganeka, right? I want to find somebody like Ganeka. Exactly like I want to find somebody like Ganeka. Then I'll find out what is your height, what is your weight, what is your skin texture, etc., etc. And I'll find a girl who looks like Ganeka. But what about what Ganeka thinks and what that girl can think? Did I explore that?
Hmm.
So when Mendeleev was doing the classification, the elements were fewer and the ways to find out their chemical properties were limited. No. So he did not know everything about all the elements, right? So he looked at some of the similarities and brought them together. Fine.
Yes.
So when they went deep into each and every element and analyzed their properties, then only they realized that these elements are different. The element molybdenum is in D block, whereas element tellurium is in P block. So maybe at that time he looked into some of the properties. Got it?
Yes.
Okay. So the best thing was that he did not bother to no deviate from the increasing order of masses to fit the properties. So for him, the matching of the properties was more important. Whatever little properties he knew, he wanted to group the elements based on the similarities in the properties and not by merely arranging them in increasing order of masses. That was one of the problem with Newland's classification, right? He did not worry about the similarities and he just went on to classify the elements and categorize them on the basis of their atomic masses, which was a wrong move. Mendeleev did not do that. The moment he saw that by following the increasing atomic mass, he was not getting the similar properties, he did not bother to swap the position of the elements and disobeying his own increasing order of atomic mass. Is it okay?
Yes.
Okay. So he generated a periodic table. Okay. This periodic table is said to be Mendeleev's periodic table. Now, we are going to learn the modern periodic table. Fine. The modern periodic table. Okay, I have to get. Okay. Now there is a tabulation about some of the elements. Well, I so it said no that Mendeleev's prediction for the elements which were not found at that time, and in his periodic table he left empty spaces and he proposed their names to be Eka aluminium, one like aluminium, and one like silicon. And he found out that this Eka aluminium was indeed gallium and Eka silicon is germanium. So he proposed that and the element Eka aluminium, which is gallium. Of course, I was actually showing scandium, I believe. Sorry, it was gallium. One like aluminium, which is gallium. He proposed the properties that its atomic mass would be 68, its density would be 5.9, its melting point would be low. Formula for oxide is E2O3, and the formula for chloride is ECl3. Taking the cue from this, they identified the element and found that it is gallium. It is another element which was named later as gallium. And when they matched the properties with what was proposed by Mendeleev, they were astonished to see that the properties did really match with his predictions. That means the Mendeleev's periodic classification is really a true way of classifying the elements, based on which we could even identify the yet to be identified element. Are we clear?
Yes.
Okay. Similarly, he predicted that there would be one element like silicon with so and so properties. And when the element was found, it was named germanium and its properties were more like what he predicted. So his classification proved to be right for a very long time, actually. Okay, his classification was taken so much so that even today, no, we celebrate Mendeleev's. I think a few years back they celebrated 150th year of Mendeleev's classification. So he is still given credit. Is it okay?
Yes, ma'am.
Okay. The boldness of Mendeleev's quantitative predictions and their eventual success made him and his periodic table very famous. Mendeleev's periodic table, which was published in 1905, is shown here. Is that okay? It
Yes,
almost persisted for around 10 to 15 years until another scientist named Henry Moseley, okay, did something exceptional. Okay, but before that, up to Mendeleev's classification for an element, the atomic weight was thought to be the reference. All the elements were arranged in increasing order of atomic masses or atomic weights. Based on this, Mendeleev also proposed a law. He said that the properties of the elements are the periodic function of their atomic weights. What is the meaning of this? When the elements are arranged in increasing order of atomic masses, the properties of the element showed a repetition. This repetition in the property is termed as periodicity, periodic function. The properties are, as the atomic weights increase, the properties get repeated. So the properties of the elements are the periodic function of their atomic weights. This was suggested by Mendeleev. Are we clear? This was said to be Mendeleev's periodic law. It was said to be periodic law that all elements behave or obey this law. Are we clear?
yes, ma'am.
Okay. Now, up to Mendeleev's periodic classification, that is Dobermeyer's, Lothar-Meyer's, Charncote's, then Mendeleev's classification, atomic mass was taken as the reference value. And for the very first time, Henry Moseley did something different. What did he do? He subjected the elements to X-rays. Remember the hydrogen spectrum and all?
Yes, ma'am.
Hydrogen was irradiated with continuous spectrum and the emission spectrum was studied, and based on the electromagnetic radiations present in the emission spectrum, the various energy levels were decided, correct? By Bohr. Similarly, the elements were subjected to X-rays. It's just one part of electromagnetic spectrum. So the response of it will be again called as emission spectrum, and the emission spectrum would carry some electromagnetic radiations because it would be discontinuous, right? These electromagnetic radiations and their frequencies were determined when a plot for the frequency versus the atomic number, square root of frequency versus the atomic number was plotted. The graph happened to be a smooth graph, a linear graph. Whereas when the same was done for atomic weight, when the square root of frequency was plotted against atomic weight, the graph was very erroneous, or maybe we can say erratic. It was not a very smooth graph. So Moseley concluded that probably the properties of the elements are not governed by the atomic weight. Probably they are governed by the atomic number. Are we clear? Where the idea of atomic number could be the basic identity of an atom came from?
And so Henry used the atomic number but not atomic weight to substitute.
Yes. And it was a significant shift in the concepts. It's a significant shift. The most vital shift. Fine.
Yes,
Okay. And the observation was when the electromagnetic radiation obtained in the emission spectrum of X-ray analysis of element were plotted against the atomic number, the graph seemed to be smooth. It was a straight line, but it was not a straight line when the same frequencies were plotted against atomic weight. So probably they thought that atomic number is a better criterion than the atomic weight. So they started arranging the group. There was not just not Henry Moseley, few more people. They started arranging the elements in increasing order of atomic number, and they looked for the repetition in the properties, and they found a lot of repetition in the properties. They changed the Mendeleev's periodic law to modern periodic law, stating that the physical and the chemical properties of the elements are the periodic function of atomic number. Is it okay? This was the highlight. In Mendeleev's classification, it was the atomic mass or the atomic weight. Henry Moseley's classification was based upon the atomic number. Are we clear?
Yes.
Just give me a minute. Okay. Now, based on this, what they did was they started arranging the elements in increasing atomic number, and they saw a lot of periodicity. They saw a lot of repetition in the properties. So wherever they saw a repetition in the properties, they kept the elements together, and thus they generated the modern periodic table. This is the long form of periodic table, or you call it as modern periodic table, which looks little more extensive than your Mendeleev's periodic table, right? The first feature, striking feature, is in a single spot you don't find two or more elements, correct?
Yes.
Okay, so this looks more organized than three or four elements being present in the same spot. Okay, now the modern periodic table comprises of some horizontal rows. These are said to be the horizontal rows, right? These are said to be horizontal rows. These are horizontal rows, and there are vertical columns. These are vertical columns. In modern periodic table, there are 18 vertical columns and 7 horizontal rows. Each of the vertical column is said to be a group. Okay, contrary to the Mendeleev's periodic table, where the names of the groups were given. Okay, actually, in Mendeleev's periodic table, the vertical columns were called as series. They were called as series. Right? This was a series. This is considered as a series. Whereas in modern periodic table, the vertical arrangement of elements is now termed as group. Are we clear?
Yes.
Hmm. In Mendeleev's classification, these series were named as 1A, group 2, Roman numeral. Remember, I told you? The Roman numerals were used, and they were termed as 1, 2, 3, 4, 5, 6, 7. And in that 6A, 6B, 7A, 7B. So in modern periodic table also, they tried to spot that, and they labeled it as 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8. You remember iron, cobalt, and nickel were placed. Even copper was placed there together.
Yes, ma'am.
Iron, cobalt, nickel, and copper. Okay, so this nomenclature was abolished. So this is no longer followed now. The Mendeleev's classifications nomenclature of these series is no longer followed. Instead, see, the inert gases, when they were identified later, were incorporated into the periodic table without disturbing the rest of the arrangement. This is the rest of the arrangement, the major part. When inert gases were identified, they were placed without affecting the existing arrangement, and they were put as group 0. Now, this system of calling them as group 0 is also abolished, and instead, all the groups are numbered continuously from 1 to 18. So, there are 18 groups and 7 periods. There are 7 periods. These periods are horizontal rows, and the groups are vertical columns. Is that okay?
Yes, ma'am.
Okay. So we will be learning more and more about the periodic table only now. Okay. So what are the why the modern periodic classification is correct? Because it is being followed even today. So what makes it so correct? We will try to understand. Okay. So the modern periodic table, I'll just copy the periodic table so that I can keep discussing. Okay. So this is your modern periodic table, right? Now look at this. In the modern periodic table, first thing you should note, as I told you, that the elements are put up as groups. And in the Mendeleev's periodic table, the hydrogen was considered as a element whose position is not very fixed, correct? Remember, hydrogen was treated as a problem, and the problem is not yet solved. It's still treated as a problem only. So, hydrogen is not found to have a correct place now, also. Why? Because last class, I think we learned that hydrogen would combine with the chlorine in 1 is to 1 ratio, same as sodium would combine in 1 is to 1 ratio. So, that made hydrogen to look similar to sodium. On the other hand, hydrogen would combine with hydrogen, like fluorine combines with fluorine. So that made hydrogen to look like fluorine. So the confusion was whether hydrogen should be put along with the sodium group or should be put along with the fluorine chlorine group. So this dispute still persists and it is given a unique place here so that that dispute is not it's not completely resolved, so you can't fix the hydrogen's position. Is it okay?
Yes, ma'am.
Okay. The next thing, when you look at the modern periodic law, it says that the properties of the elements are the periodic function of their atomic number. The atomic number tells you the number of protons. The number of protons is equal to the number of electrons. And when you take the electrons and write the electronic configuration for some elements, let us try doing that. For example, lithium in the group 1. Lithium, sodium, potassium, rubidium, cesium, and francium. So we'll write at least for some. Lithium, sodium, potassium. We see that it is 2, 1, 2, comma 8, comma 8, sorry, 2, comma 8, comma 1, and 2, comma 8, comma 8, comma 1. Why do you think lithium, sodium, and potassium are placed in a single group form?
It has same valence.
Very good. And because it has same valence electrons, can we say that they will all have similar properties?
Yes, ma'am.
Yeah. So why lithium can lose one electron, sodium can lose one, and potassium also can lose one. So that means the atomic number is better than the atomic weight. Lithium's atomic weight is 7, sodium's atomic weight is 23, and potassium's atomic weight is around 39. What is conveyed from these numbers? Is it not number of neutrons plus protons?
Yes, ma'am.
And the number of neutrons and protons do not even participate in the chemical properties. Na? It's only the electrons which are responsible for the chemical properties, how many electrons to lose, how many electrons to gain or share. So neutrons and the protons have no say in the chemical properties. So why to take unnecessarily atomic weight? And that's why the classification was going wrong for so many years. Are you getting the point?
Yes,
Okay. So atomic number. Now that we know the configuration in terms of SPDF, in terms of orbits, orbitals also, it is very easy to look for the electronic configuration. Look for lithium, whose atomic number is 3, 1s2 and 2s1. Sodium, whose atomic number is 11, is 1s2, 2s2, 2p6, 3s1. Potassium is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Now tell me what is common among all these elements? Can we say that they are receiving their electrons in ns1? Can I put it as ns1?
Yes, ma'am.
Okay, so all the elements in the first group obey ns1 configuration. So all the elements in group 2, look at them. It's beryllium, magnesium, and calcium. So if I want to write and I don't want to waste the time, then I'll just quickly change to beryllium, magnesium, calcium, and shift this. See, beryllium, magnesium, calcium with 4, 12, and 20. Isn't it 1s2, 2s2? Here it is 3s2, here it is 4s2.
Yes, ma'am.
So can I say that the general configuration for group 2 elements will be ns2?
Yes, ma'am.
Is there any other possibility of having ns3?
And would it come in the third row?
No. Will it be possible to put a third electron in the s subshell?
No, ma'am.
So is it that means the story of the s subshell is over, na?
Yes, ma'am.
Now these two groups, group 1 and group 2, which receive their electrons in the s subshell, are also called as s block elements. Is that okay?
Yes, ma'am.
Okay, just a minute. Yes, Netra. Netra, yeah, I just wanted to know in the last 2 weeks, which class did we cancel, ma? Okay. Now, see, so this was said to be S block. Now, coming to the next case. Look at this configuration. This is very peculiar. எங்க the start பண்றோம் and where we are ending. Can you see that? We are starting with S. And if you see the last element, it is 4p6. I want you to focus on one single period and see where it ends, Ganika. See, we started this fourth period with 4s1, correct?
Yes, ma'am.
And where are we ending? We are ending at 4p6. Similarly, look at the other groups. Sodium or rubidium, where are we starting? We are starting with
5 S, ma'am.
5s1 and we are ending with what? Xenon is 5s2,
5.
5p6, correct?
Yes.
Actually, this discussion will help you to tell how many elements are possible in a particular period. இப்ப discuss பண்ணோம் இல்லையா? This will help us to know how many elements are possible in a particular period. Is it okay, Anna? It looks little irregular, na? It looks
Yes.
little irregular, correct? Okay. This discussion will help us to tell how many. Okay. Now, let us just see. After some time, maybe we'll explore that. But let us go to lithium and beryllium are receiving electron in 2s1 and 2s2. Let us go to boron. After 2s comes what? Can we see? After the 2s is completely filled, I have to go to 2p. So are we not following this Kanika 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f? In a way, are we not following that? I'll make you understand that it is the same. But at least after 2s, are we not filling the 2d, 2p?
Yes, ma'am.
Okay, see here, 6p. I'm going to write because I'm going to use all of these. 6f is not at all going to be used. 7s, 7p will be used actually. All the elements that we have today are using only these many orbitals, even though others are there. So we have something called as 6f. We have something called 7d, 7f. We have got 5g, 6g, 6h. You have got 7g and so on. But the blue ones are the ones which we are actually using. Okay. Now come to this. So what did we do? We did hydrogen and helium. Hydrogen is what? Hydrogen is basically one electron system. So we'll take hydrogen has 1s1, helium has 1s2. That makes the first period complete. That makes the first period complete. So in the first period, only the first shell components receive electron. Are you okay with this fact? In the first period, only the first shell, subshells receive electron. Is that okay?
Yes,
In the first shell, what do you have? Only the 1s. So 1s only receives the electron. So in the second period, the 2s and 2p receive the electron. What did I say? On the left, we start with s. On the right, with end with p. On the left, we start with the s. And on the right, we end with the p. So 2s and 2p. That's the end of the period 2. Are we okay with this?
yes, ma'am.
Okay, now I'm going to write something more. So this is 2s and 2p. How do we fill up the electrons? Remember, we fill the electrons like this. We go for 1s, then we go for 2s, and then we go for 2p, correct? After 2p, where do we go? We go to 3s, correct?
Yes,
But
ma'am.
the second period will start with the 2s and end with the 2p. So I will do what? I'll cut only 2p and say that the second period is over. Are we clear?
Yes, ma'am.
Are we clear? So 2s and 2p. And I'm going to cut the 2p and I'm going to say that the second period is over. Now, in 2s, how many electrons can be fit? And in 2p, how many electrons can be fit?
2s, 2 electrons.
And 2p? P, in any case, in any shell. S can have 2, P can have 6, D can have 10, and F can have. Yes, Kanika,
We can, ma'am.
14, na?
Ma'am, could you tell me?
Kanika, your voice is not audible to me.
And is it audible now?
Yeah. Tell me your doubt.
No, no, I was not able to tell because of the.
You are not able to.
I was not able to tell because of the network issue. But
Okay. But is the fact okay for you?
yes, ma'am.
Okay. Now see, in the case of P, how many electrons?
6.
6 above. See, can we see here that it is 2s1? Keep no writing the electronic configuration in mind. It is 2s1, 2s2, followed by 2s2, 2p1, 2s2, 2p2, 2s2, 2p3, 2s2, 2p4, 2s2, 2p5, and 2s2, 2p6. Are we clear?
Yes, ma'am.
So, can we say that there are 6 electrons in P And therefore, we will have a P1, P2, P3, P4, P5, and P6. So 6 elements in this block containing the electrons or receiving the outermost electrons in the p subshell. Can we say that?
And will you repeat it again?
I am saying that, see, lithium is 2s1, beryllium is 2s2. One more electron, where it will go, ma? If 2s2 is fully filled, where it will go?
2p.
2p. So 2p1. Then carbon has one extra electron. Where it will go?
2p2.
Nitrogen,
2p3.
oxygen,
2p4.
fluorine, 2p5,
2p5.
neon, 2p6. So I told you the period starts with S and ends at P. So how many elements are there which can receive electrons in their P subshell? 6. And that's because P can hold 6 electrons only, no?
Yes, ma'am.
Understood? Now,
Yes.
so can we say that all these elements are receiving electrons in their P? Look at it in expanded form. Look at it. What is common between boron and aluminium? If boron is 2s2 2p1, what is aluminium?
3s to 2p.
3s2 3p1. Gallium 4s2 4p1. Indium 5s2 5p1. Thallium 6s2 6p1. Nihonium 7s2 7p1. Are we clear?
Yes, ma'am.
So is it not right that all these elements have got same type of outer electronic configuration and therefore they are all chemically similar?
Yes, ma'am.
Okay, and can we see that all these elements, excepting helium, of course, all these elements are receiving their outermost electrons in the p subshell? So can we call this as p block elements?
Yes, ma'am.
The earlier one was called as what?
S block.
S block, because the valence electrons were going into the S subshell. Here the valence electrons are going into the P subshell. Okay, done. Now see again. We have finished the first period and second period.
Ma'am,
Let us come to third period.
and one doubt.
Yes, tell me. Yes, tell me.
And so the p block, all the elements has its valence electron in the p cell. So it's not
Yes,
p block.
yes, yes. The valence electron is going. Where is the last electron going? Is the question. Supposing chlorine is a P block element. Let us write the electronic configuration. 1s2, 2s2, 2p6, 3s2 and 3p5. We have learned 2, 8, 7. Where is the last electron going? Is it not going into the 3p?
Yes, ma'am.
So chlorine is a P block element.
Yes.
Okay, now, wonderful. Now see, now the first period contains, the first period is going to contain period number 1 is having electrons in only 1s, which can be only 2, na? 1s can contribute only 2 electrons, right?
Yes, ma'am.
Okay. The second period, period 2, begins with 2s and ends at 2p. How many electrons there then totally?
6.
6 in 2p, but 2 more in 2s, da?
8.
8. So 8 elements. Count the 8 elements. Lithium, beryllium are receiving their electrons in the 2s2, 2s1, 2s2, and then 2p1, 2p2, 2p2 up to 2p6. So these are the 8 electrons, 6 elements here and 2 more elements here. So in the period 2, how many elements will be there? 8 elements. Is that okay?
Yes, ma'am.
Okay, now coming to the next. Any period will start from S and end at P, correct? So after I finish the 1S, 2S, 2P, then I'll have to restart at 3S and go to 3P. So in the period 3, can you tell me how many elements are possible? Which subshells are receiving electron? It
S
starts
and
with
P.
3S, S and P. So it is 3s and 3p. How many elements do you expect then?
Same 8.
Same 8. So see there, sodium 3s1, 3s2, aluminium 3p1, to argon 3p6. So totally 6 again here and 2 again here. So period 3 will contain how many elements? Totally 8. Is that okay? Now we
Yes.
see more elements in group 4, period 4, sorry. We see so many elements in period 4. Shall we understand why?
Yes.
I told you any period will start with S. So I have to now start looking for 4S and end at 4P, correct?
Yes.
Apo 4S kaprama, what will I fill, ma? After 4S, according to this order, what will I fill?
4. 3D.
3D. Very good. And after 3D, what will I fill? 4P. So the period
Yes.
starts with 4S and ends at 4P. But in between, how many electrons came in?
80.
18. And that's why you have 18 elements in the period 4. So it is 4s1, 4s2, 3d1 to 3d10, and then again 4p, because after 3d we'll again go to 4p. So 4p1 to 4p6. Are you able to understand that the fourth period will have totally 18 elements?
Yes.
Can you tell me in fifth how many will be there? I have to start with 5s and end at 5b. How many elements will be there?
Uh, Same 18.
Same 18. Because what are the things which are getting the electrons? 5s, 4d, and 5p. So same 18. Now come to the sixth period. We'll start with the 6s and end at 6p. Think about it now. After 6s, the electrons go into
4F.
4f. Then
5D. 6D.
yes, 5d and 6p. So S will contribute 2 electrons, 2 elements. F will contribute 14 electrons, so 14 elements. D will contribute 10 electrons, so 10 elements. And P will contribute 6, so 6 elements. Totally how much?
30.
32. Okay, so we will look for it. Seventh period. Again, we'll finish this and go. 7s. After that, what? 7s. Then,
5F.
5f. Then
6D.
6d and
7.
7p. So this also should be totally 32, correct?
Yes.
Very good. So that means, can we say it is 2, 8, 8, 18, 18, 32 and 32, correct?
Yes.
So can we see in the period 4 and 5 there are 18? 18 groups, 18 elements, correct?
Yes.
Okay. So in fifth also same, 18 groups, 18. But in sixth, do you see there is a break after 57?
Yes.
And why is it? I told you the elements are placed along with one another when their valence electrons are going into the same subshell, correct?
Yes.
In yttrium, Y, the element named Y, the electron goes into the 4d1. In lanthanum, it goes into the 5d1, no problem. But after lanthanum, when we come to cerium, the next electron goes into the 4f, which is not like the next, no. This entire block is receiving electrons in which subshell, ma?
Yes.
It is S or D. Which gets filled first? The 4S
First
or
is
the 3D?
Uh, 4s.
4s. அப்போ 4s is already filled. அப்போ இங்க growth நடக்கிறது D ல தானமா நடக்கிறது. See,
Yes.
with here and there anomaly, but it's by and large what 4s2 is fully filled, fully filled, fully filled, fully filled. The growth in the number of electron is only in the 3D. Realize that?
Yes.
So the entire block of this yellow is actually receiving the electrons in the D. So they will be calling it as D block. Got it?
Yes.
Apo, the 58th element, which happens to be cerium, is getting the electron in 4f. So does cerium, right, show similarity with the D block?
No.
No. Its behavior will be totally different because starting from cerium, the electrons are filled in the F, F1 to 14. And this behavior is not there in the D block. D block is receiving electron in the D subshell. So how can an element receiving electron in F subshell be of same type as D subshell? An element receiving electron in D subshell. So should they be closely put? Should they be put together? Can cerium be placed along with the D block elements?
No.
And therefore, the 14 elements which receive their electrons in 4f, 4f can have 14 electrons. So progressively 4f with some irregularity is filled up. So 4f1 to 4f14, and all these elements are placed forming a separate row which is said to be lanthanoids. It starts with lanthanum actually. It starts with this star marked lanthanum. So we say lanthanum to lutetium. They form the lanthanoids. Similarly, element actinum. After actinum, you see, after 89, the atomic number suddenly shifts to 104. So where are the in-between elements? The in-between elements are here. Why? Because they are receiving their valence electrons in 5f. So it is wise to put 4f and 5f together, right? But it is not good to put 4f along with the D, na?
Yes.
That's why a set of 28 elements sit separately, which cannot be accommodated. If you see some of the periodic tables, they would have shown, interestingly, I'll just browse and see. Some of the periodic tables will show even F block sitting in the main one. That's very rarely used, okay? That's very rarely used. Shake for another. Very rarely. That's why you won't find it, okay? But if you have to show, we'll see with the hint. See, this is what I was saying. Can you see?
Yes.
This is how the longest form of the periodic table should look like. This one. Is it clear? But only
Yes.
thing, you will not have the groups. The group names are not allotted for these elements. They are allotted for lithium group 1, beryllium group 2, group 3, titanium group 4. They don't get the group numbers. But strictly speaking, they should be here. Are we clear?
Yes, ma'am.
Okay. Right. Anyhow, this table is not used. In fact, we use the traditional table like this. Fine.
Yes.
Okay. What else? What else? Let us see.
One doubt.
Yeah, tell me, ma.
Ma'am, in the D block is written as a 4s2 3D, but we know that first 4s is filled, then only 3D. So
Yeah,
at
that is only the
electron,
sequence of filling. Does it mean that the 4s moves inside and the 3D remains out?
mm,
No, na?
yes,
If this is the third shell and this is the fourth shell, this is part of the third shell. 3D is part of third shell. So why to put it in later? It is here only, no? It's only
yes,
the
ma'am.
sequence of filling which is changing, not the position of the orbitals.
Okay,
Understood?
yes. So
Ah,
as the
okay.
4s is filled first, then only 3D.
Yes, yes,
As
yes,
the electrons are at the D shell, it is known as the D.
yes. And we are following that N plus L rule to fill up the orbitals in increasing order of energy. So 4s is indeed having lower energy. That receives that means what? After 3p, in the same shell, there is a 3d0. After 3p, argon is 3d, 3p6, na? So
Yes, ma'am.
3s2, 3p6. 3d is kept 0 and suddenly the electrons go to 4s2. Once 4s2 is filled, then only electrons come into the 3d. So just because of the sequence is different, the position of the orbitals doesn't change. Okay, Ganika.
Yes, ma'am.
So is it not fair to write the 4s in the outermost part? Part
Yes,
of the outermost shell. Okay, next. See, so this was S block, which contained purely metals. Remember? Sodium, potassium, calcium, magnesium, etc. These are very, very reactive metals, correct?
yes, ma'am.
Okay. These are non-metals. We would have heard oxygen, fluorine, nitrogen, phosphorus, sulfur, chlorine, bromine. So can we say that this side is non-metal zone and the left is metallic zone?
Yes,
Okay. Now what do these do? The elements in between are not metalloids. These are only metalloids. Okay. Silicon, germanium, arsenic, antimony, tellurium, polonium, astatite. These are only the metalloids. But the transition, these are called as the D block elements are also called as transition elements. The D block is also called as transition. Why transition? Because probably these bear the change of metallic property to non-metallic property. Slowly they are actually going for non-metallic. Metallic property changes over to non-metallic property. For example, a simple case I'll tell you. Some Fe2O3 is not ionic. It behaves like a covalent compound. You put it in water, do you get O2 minus ions?
yes,
They slightly behave like covalent compounds. So the transition elements actually bear the transition. Transition means change. Change of metallic to non-metallic property. That's why they are called as transition elements. Clear?
yes,
And in between 57 and 72 and 89 and 104, there are inner transition. These are some more. They are said to be inner transition elements. They are F block elements, or you call them as inner transition elements. Are we clear?
yes, ma'am.
Okay.
And what is that means inner transition?
What are they? What are inner? Those elements which receive electron in their F subshell are said to be inner. Why inner? I'll tell you. See, say for example, in this case, cesium is receiving the electron in the sixth shell, 6s1.
Yes, ma'am.
Lanthanum is receiving in its 5d1, inner one. Cerium is receiving in the 4f, which is even inner to the 5d. Na?
Yes, ma'am.
So progressively the electrons are filled in the inner zones. So we call it as inner transition elements. Got it?
Yes,
Okay. Then now with the general electronic configuration, we shall complete the class. So what would be the general electronic configuration of S block? S block shows a variation in terms of NS1 and NS2. So we'll put it as NS1 to 2. That's the range. Okay. This becomes the general electronic configuration. Come to P block. In P block, the S is completely filled. Na? So can we put it as NS2? What is getting filled is NP126. Got it?
Yes.
Okay. Come to D block. In D block, look at some of the elements. They are very interesting. Chromium. See, normally everyone will have 4s2, 4s2, 4s2. But we have learned abnormal electronic configuration of chromium and copper, remember?
Yes, ma'am.
So, can we say 4s can have 1 or 2?
Yes, ma'am.
Okay. Also, look at the element palladium. It's a very special element. And compare its configuration with nickel and platinum. If nickel is 3d8 4s2, what should have been palladium? It should have been 4d8 and 5s2, na?
Yes, ma'am.
But for some reasons, it is both the electrons of S are going into the 5s. 4d, sorry. 5s is going into the 4d. So the configuration is 4d10 and 5s0. So because of this element, the S can even be 0, right?
Yes.
Okay. So 4s ranges from 0 to 2. And the inner 3D ranges from 1 to 10. Correct?
Yes,
I
ma'am.
can put this as n value and this as n minus 1. Any problem with that? If 4 is
Briefly,
n, then 3 is n minus 1. Inner shell. Okay?
could you repeat it again?
No, I said that if you look at the palladium family, this row, then isn't it 4D 1 to 10 and 5S 0, 1 and 2?
Yes, ma'am.
Can I put this as n, the highest principal quantum number in the entire period? Will this 4 not be termed as n minus 1 then?
Yes, ma'am.
So can we generalize and write it as n minus 1D 1 to 10 and ns 0 to 2?
Yes, ma'am.
That becomes the general electronic configuration of the D block elements. Clear?
Yes, ma'am.
Similarly, look at the F block elements. What will the cerium have? Cerium has a 6s2. Correct?
Yes, ma'am.
So, and none of the elements have got 6s1. See? Does any element have 6s1?
No, ma'am.
No. So I'll put it as ns2, 6s2. Then come to the 5D. 5D contains either 1 or 0. See, 0, 0, 0, 0, 0, 0. Here it is 1, but not more than 1. So can we say 0 to 1?
Yes,
And 4F, more importantly, 1 to 40. It's very understandable because the elements, the lanthanoids are present here. So in the period, the 6s is getting completely filled. 5D is 1 or 0 and 4F ranges from 1 to 40. We don't have to worry after this. Before this only we should see na, to write the electronic configuration of F block elements. Clear? So 6s is
yes,
fully filled. 5D can be 0 or 1 and 4F is definitely varying from 1 to 40. Okay, in general, if I have to put, can I put it as NS2 This will become n minus 1 d 0 to 1. And this will become n minus 2 f1 to 14. So this becomes the general electronic configuration of the F block elements. Are we clear?
Yes,
Okay. So with this, we will stop the class. Okay.
ma'am.
Again, I'll tell you. Tell me.
Could you just show the general one of the D block, ma'am? I will note it down.
Yes. This is for the P block. This is for the S block.
Yes, ma'am. Yes,
I think I will not be available on 4th March. Okay. So what we will do going forward, I'll call you for classes on Sundays. Is that okay? We have missed some classes in last week also. And upcoming week 4, I need to go to Bangalore. But 6th will be possible. Even after that, if I miss some classes, what I suggest is we will start having classes on Sundays. So you and Shri both, you will have to check and tell me what time will be comfortable for you so that we can make up for whatever classes we have missed. Okay?
okay.
Yeah, okay. So when Shri comes, I will discuss. So next week, we will have class on 2nd. 2nd is not a problem. 6th is not a problem. 4th, definitely I'll not be. Okay? Okay. Yes, ma.